Today I'm here to talk to you about how we use the big data approach to scale a familiar performance analysis technique such as critical path analysis to large-scale, complex websites like Facebook. So Facebook is a complicated website. And to show you some of this, I've shown you here a waterfall chart of the loading of a single Facebook request. Now, as you can see, the single Facebook request shows the massive scale of Facebook. So the loading of a single Facebook request involves many tasks and parallel execution of many components. I'd also like to point out the heterogeneity of the system. So each color of these boxes here represents a different type of execution. So you have your PHP execution, your JavaScript execution, bytes being put down on the network. And so these two factors, scale and heterogeneity, make analyzing performance very challenging. And so if I were to look at a single request like this, I might have certain performance questions, such as, what is the component that's the bottleneck of this request? Or what is the critical path of this request? So I've shown you the critical path here, but actually the information here shown on this waterfall chart isn't enough to derive this critical path. What we're missing are the causal relationships between these segments, or the dependencies between these segments. And so today I'll be talking to you about our technique to derive these causal relationships in a large-scale heterogeneous system like Facebook. And so our approach has 4 steps. We first need to identify the segments that were executed during the request. So we need to basically come up with this waterfall chart that I've shown you. From there, we infer a causal model of our entire system using a large number of these traces. And once we have this causal model, we can then apply it to individual traces and do these types of analyses that I was talking about earlier, such as what is the bottleneck, or what is the critical path of a single request. And after we've analyzed a single request, we can do this repeatedly over a large number of requests and build up statistics about our entire system and get performance statistics about our entire end-to-end system. And so as I said, in order to do these performance analyses, we need a causal model of our entire end-to-end system. Now we can use previous approaches where we could go in and instrument the entire Facebook system. However, this would require a huge amount of effort as we need to instrument every single type of scheduler or all the communication between these components. Alternatively, we could go through and collect all the Facebook engineers and put them in the room and have them draw up a model of our entire system. However, this doesn't scale well as our system changes. And so what we need is a method that works well at scale and with the large number of heterogeneous components we have in our system. However, we can make use of 2 key properties in these large-scale systems. We noticed at Facebook that these components already had an extensive logging infrastructure. However, these logs are all in a different format. And so if there's some way that we could aggregate these component logs together, we could gain a tremendous amount of detail about a single request execution. We also noticed that Facebook handles a large volume of requests. And so even if we sample at a low sampling rate, we can gather a large number of empirical observations, and we can observe behaviors that even occur infrequently. So using these 2 observations, we can apply a big data technique to performance analysis. And so today I'm here to talk to you about the mystery machine, which infers a causal model from a large number of traces. And we first do this by identifying what segments must be executed in the request. And then we hypothesize all possible causal relationships among these requests, among these segments, such as happens before relationships or mutual exclusion relationships. And then we can iteratively refine this causal model by looking at individual traces and observing counterexamples to these hypotheses and rejecting them. Finally, once we have this causal model, we can use it to analyze specific requests and do these types of analysis, such as critical path analysis, that I've outlined at the beginning of the talk. So I'll now talk to you about how we first identify what segments must be executed. So we asked ourselves, well, in order to do this type of performance analysis, what is the minimum amount of information that we need to do this? And so in a single Facebook request, there are multiple tasks that get executed. And a task is simply just an independent component of the web page that gets executed as the page gets rendered. And within the task, there are events that must be executed throughout the duration of this task. And each event is unique throughout the duration of the request, and it maps exactly to a specific log message in these component logs. And so we can define a segment of execution as being the interval of time between two unique events in a task. And so what we found in aggregating these component logs is that even though they all had a different format, they already had this minimum amount of information in them. And so what we can do is we could unify these component logs using this minimal schema in order to gain a detailed end-to-end trace. And since we used existing component logs already, it only took about 1 month's worth of work to gain these detailed end-to-end traces. And once we have these traces, now we can go to our next step of our approach, which is to infer a causal model from a large number of these traces. So as I've said, we hypothesize all possible causal relationships between the segments that we've identified that have executed. And then we go through a large number of traces to iterate through our causal model until we finally converge on the final causal model. And so when I talk about these causal relationships, we currently look for 3 types of causal relationships in our system. The first is a happens before relationship, where a segment B must wait for segment A to finish before it can proceed to execute. The second is a mutual exclusion relationship, where 2 segments might contend for a lock and thus must be mutually exclusive. The third type of relationship is a pipeline relationship, where segments must follow a FIFO order among tasks. And these relationships must either hold or they don't. And so if we ever see a single counterexample in a trace, we know that these relationships will be invalidated. And so now I'll briefly walk you through an example of our iterative refinement approach in a simple system that consists of 6 components. And for simplicity's sake, I'll only consider happens before relationships. And so in our initial starting state of our system, we see our 6 initial components, and we've assumed every single happens before relationship between every pairwise component. And now we consider an empirical trace that we've gathered, this end-to-end trace, and we see in this single trace that there's already a whole bunch of counterexamples that we can eliminate from our model. So we see, for example, that segment S2 has been executed after S1, and so we can eliminate that happens before relationship. S2 happens before S1. And so we go ahead and do this and remove all other counterexamples that we've seen in this one particular trace. And now we look at another trace. And in this second trace, we see that there's a relationship that's been invalidated in this trace that wasn't present in the first trace. So we see that N1 and N2 execute concurrently. And so now we can remove the happens before relationship. N1 happens before N2. And so we can continue to do this for millions and millions of traces until we finally converge on a causal model. And then for simplicity's sake, we apply a transitive reduction to present a simpler causal model. So we did this for approximately 1.3 million traces that we've gathered across 1 month of Facebook traffic. And this was for the main Facebook page. And this entire work is actually parallelizes quite well. And so even though we looked at over 1 million traces and hundreds of thousands of relationships, it only took us about 2 hours to run on the Hadoop cluster. And we can run this every night as a batch job and produce a new causal model every day. And so now that we've produced our causal model, we can now use this causal model to apply it to analyze individual traces. So we can answer these questions that we posed about a single trace at the beginning of this talk. And so again, I go back to my example where I have this causal model that I've derived. I'm looking at the first trace that we looked at. And so to find the critical path through a trace, we simply just inject the dependencies that we found from our causal model into this trace. And then we can apply a standard longest path algorithm to find the critical path. And we can see for a single trace what the breakdown of the latency was. Now we can go back and look at these 1.3 million requests that we sampled over 1 month. And we can build up statistics about our entire system. And so now we can answer questions such as, what is the latency breakdown of a request? What what does a specific component contribute to this end-to-end latency? But first, I'd like to show you what would happen if we tried to answer this question without a causal model. So in our naive approach, what we did was sum up just the latencies of all these components and looked at the breakdown. So what we did is we categorized each of these components into 5 broad categories and broke down the latency as such. And now if we compare this to the latency as we look at it through the critical path, we see that these distributions are significantly different. So you see the server portion of the latency is actually twice as much in the critical path. So in our naive approach, we are underestimating the importance of the server latency in the end of the request. And similarly, we've similarly overestimated the importance of the network in JavaScript for these end-to-end requests. So the takeaway here is that we actually need a causal model to correctly understand the latency because of the concurrency in our system. Now, what I've shown you here is for the average Facebook request. Then we asked, so this holds true for the average Facebook request. What we'd like to know now is, does this hold true for every single request? Well, actually, it turns out the breakdown in critical path shifts dramatically across requests. And so what I've shown you here are 3 CDFs breaking down the percent of the critical path that each one of these categories, server, network, and client, make up this latency. And so for example, you have your server, and we want to say, and so we see that the bottom 20% of these requests, the server contributes 10% to the end-to-end latency. But on the other end of things, we see that for the top 20% of requests, the server contributes 50% or more to this end-to-end latency. And this variance holds true for both the network and the client as well. And so you can see that the server, network, or client at any point in time can dominate this latency. And intuitively, this actually makes sense since Facebook is being accessed by a wide, diverse user base. So take, for example, you have a user who is a very fast network or client. They would be able to consume bytes as fast as possible, as fast as the server is able to generate these bytes, and they are bound by the server in terms of how fast they can load the page. Now take, for example, you have a user who's still on dial-up. These are the users where the network dominates more of their latency. So the bytes will get queued up in the network, and now they are bound by their network in terms of how fast they can render the page. Finally, we have users who are still using old computers. And so these users will be bound by how fast their client can render the JavaScript of the Facebook page. And so they're literally waiting for their computer to load Facebook. And so now that we see that the end-to-end latency actually depends on different characteristics of the client and the network, we can make a potential scheduling optimization on the server. We can group users into 2 categories. We have the first group of these slow users who are networked or client bound, and we said that they have slack in their server generation time. That is, if we produce data slower on the network, on the server, the end-to-end latency actually stays the same. And then we have another group of users, these fast users, where there's no slack in the server generation time, where if we produce data faster, we can decrease the end-to-end latency. And so this potential scheduling optimization is to deliver data when it's needed to the user as opposed to as fast as possible and reduce average response time. Now, undertaking such a optimization would actually require a huge amount of effort to modify the entire Facebook infrastructure, and it wouldn't necessarily be clear as to what if there would be a huge benefit. And so now we can go back to the Mystery Machine and look at our other types of analyses. So we have a slack analysis, where slack is defined as the amount of time that we can delay a component by before it appears on the critical path. And we also have a what-if analysis, where we can use this large data set that we've gathered and look at the natural variations in the amount of time that the server spent generating a request, and use that to simulate a slower or faster server and see what effect this will have on users. And so the 2 key what-if questions we want to answer are, for these slow users, if we slow down how much time it takes the server to generate their content, would this actually not affect their end-to-end latency? And for these fast users, if we do speed up their server generation time, will this actually lead to a decrease in end-to-end latency for these users? And then if that's the case, can we actually predict what type of connection that these users will exhibit? Can we predict at the time of receiving a request if a user is slow or if a user is fast? And so the answer to the first question, we grouped our users into two categories. On the left, I've shown you these fast users who have very little server slack. And on the right, I've shown you the users who have a lot of slack, so these slow users. And so on these graphs, on the x-axis, what I've plotted is the server generation time, or how much time it took the server to generate a user's actual page content. And on the y-axis, I've shown the end-to-end latency, which is the entire time it takes for the user to load Facebook. And so you can see for these fast users, the requests clump up near the line y equals x. And so you can see a commensurate increase in the server generation time will lead to an increase in end-to-end latency for these fast users. Whereas for these slow users, you see that as we increase server generation time, it's just kind of like a blob. There's no really clear effect that server generation has on end-to-end latency. And so this proves to us that Slack actually is a good measure of indicating to us how well server generation time affects end-to-end latency. Now, as I said, Slack is only calculated after a request has been processed. We don't know Slack ahead of time, so if we were to actually implement such a scheduler, we wouldn't be able to use Slack as a metric to predict whether a user will be slow or fast. So we tried to look at other features that were useful in predicting Slack. So we looked at the user's browser type or the user's operating system, and it actually turns out that the best predictor of Slack was past Slack. And so we went back to our data set, and we looked at repeat users that we sampled twice. And we calculated the Slack for both their visits to Facebook, and we plotted this against each other. So on the x-axis, I've shown is the Slack for their first visit, and on the y-axis is the other Slack for the repeat visit. And you can see these. So as you can see, these requests are on or near the line y equals x. And so you can see that past Slack is quite representative of future Slack. And so if we just use a simple classifier to classify these users, where we say a user who has more than half a second of Slack is a slow user, and a user who has less than half a second of Slack is a fast user, we can correctly classify these requests 83% of the time. Now, we do mispredict that users will have Slack available 8% of the time, and we miss opportunities for optimization 9% of the time. But this does prove to us that it is actually quite feasible to build such a predictor and to use Slack as a metric for the scheduler. So today I've talked to you about the mystery machine, which takes a four-step approach to applying these performance analyses to a large-scale heterogeneous system. We first identified what segments must be executed through a request. Then we infer the causal model using a large number of requests. And then using this causal model, we applied it to look at individual requests. And then we looked at a large number of these individual requests to build up statistics about our entire end-to-end system. So thank you for listening to my talk. I will now take any questions you guys have.
Hi. My name is Greg Hill from Stanford University, and I was just wondering, you're kind of aggregating these logs from different machines, and then inferring a causal model from them. So how are you dealing with the clock drift between the machines?
Right. So there are details about this, about how we do this in the paper, the exact details. But we essentially get an estimate of the RTT between either like the client and the server, and then we assume that that the RTT is symmetric between the client and the server, and we actually look at repeat requests between the same client and the server, and we take the minimum RTT estimate that we have of all these requests, same repeated communications between the server and the client. To count, and then we calculate the clock drift between the server and the client.
What about just like within services? So let's say just one of your Memcached servers is 2 milliseconds behind. Like, how do you make sure that you're not inferring that something happens before something else?
So within a single machine, we assume that the clock is consistent within just a single machine.
Okay. So you're doing the RTTs between every.
We do the RTTs between every single RPC call between services. Yeah.
Haryadi, University of Chicago. Nice work. I have a question regarding your what-if analysis. When you delay the client or the server, how much guarantee that you provide in your prediction? Because I know in these sophisticated systems, there are lots of like timeouts, failover recovery, and so on. So although you see delay, maybe in real life, if you see more delays, that thing might have been failed over and it might be fine.
Right. So in our what-if analysis, we're actually just taking the natural variance that we find within our large data set. So this considers, the variance on the server load, or the number of friends that a user might be, that a user has, right? All these affect the server generation time, and so all that's already taken into consideration in our large data set, right? This is a natural variation in the server processing time.
All right, thanks.
Inge from Columbia University. I know there's a lot of related work in this area. So what I can name is Magpie in OSDI 2004, Web5 in 3W 2007, and Rake in WQS, and also Xtrace in SDI. How do you compare with them?
Right. So all these systems, as I've said at the beginning of my talk, we're dealing with this large-scale heterogeneous system at Facebook, and like these methods work great, in homogeneous systems, and but what we really want to do is we wanted to get this analysis up fast, and so what we did is we just took these existing component logs that these users already had that you made use of these methods, right, and we were able to unify them together and apply this big data approach to get the same type of analysis as these services offer, but
what's new in your techniques? For example, like Mag5, also your causal relationship between those logs. I mean, it seems very similar.
Right. So we're providing the same type of analysis that they're doing, right? But in terms of like implementing these types of systems at Facebook would require a huge amount of effort, right? I'd still be there, going through every component, instrumenting every single component, and going through and as opposed to being here today and talking to you about like the analyses that we've
So it's like
done.
implementation contributions, like we mentioned in the big data you are using.
Well, I think it's exactly what I said. These contributions.
Okay, sure. Thank you.
Ryan from UC San Diego. I'm wondering, presumably there could be some inaccuracy in the trace data, and how will that affect the analysis and the model, and how does the system handle it? Thank you.
Right. So you're right in that in terms of that there are certain inaccuracies in the lower level sort of logging messages, then it would affect some of our analyses like critical path analyses, where we might assume that there's more concurrency in our system than there actually is, or if there, we might just assume that there's more concurrency in the system than there actually is. In the case where if we're missing log messages, when we build our model, when we build our model, even if there are missing log messages, the relationships that we do have, that we observe, still hold true. We just might be missing information that just never is logged, so there's nothing that we can do about that.
Very quick question.
Very quick. Alexander from Parallels. Do you have situations when you when you need to track timestamps on different hosts in single task? And if yes, how do you synchronize time on servers?
Right. So this is this is exactly how I described in the first question, where we deal with clock skew across these servers. There's more details in the paper. I just didn't have time to talk about it in this talk.
Okay, let's thank the speaker once again.